In this video, I'm going to recap how eigenvalues are defined and go on to show how to find them for a 3x3 matrix. First, let's remind ourselves of what eigenvalues are. This is discussed in some detail in my previous video, Eigenvalues and Eigenvectors, so I'm just going to summarize how they're defined here. Given a square matrix A, the eigenvalues are scalars lambda for which we can find non-zero solutions to the equation ax equals lambda x, and the corresponding vector x is known as an eigenvector. We can rewrite equation 1 as ax equals lambda ix, where I is the identity matrix, giving us a minus lambda I times x equals the zero vector. Now, we know that x equals 0 is a solution to this equation. Thus, for non-zero or non-trivial solutions, we require the determinant of a minus lambda I to be 0. This is what we call the characteristic equation of A, and the left-hand side of the equation is known as the characteristic polynomial. Now, before we proceed, we need to remind ourselves how to find the determinant of a 3x3 matrix. Given a 3x3 matrix A, such as the one shown here, the determinant is calculated as follows. We first take the first element of the first row and multiply by the determinant of this submatrix, giving A11 times A22 times A33 minus A23 times A32. Then we take the second element and subtract this value multiplied by the determinant of this submatrix, giving A12 times A21 times A33 minus A23 times A31. Finally, we take the third element multiplied by the determinant of this submatrix, giving A13 times A21 times A32 minus A22 times A31. The method can of course be extended for higher dimensions. It gets increasingly complex to write down, but follows the same pattern. Okay, let's look at an example. We want to find the eigenvalues of the matrix A given here. First, we write down the matrix A minus lambda I, giving us this matrix. Next, we need to find the determinant. The first element is 5 minus lambda, and this will be multiplied by this determinant, giving us 5 minus lambda squared minus 40. Next, we move across to the minus 10, giving us plus 10 times this determinant, giving minus 16 times 5 minus lambda plus 80. And finally, we have 5 times this determinant, giving minus 160 plus 20 times 5 minus lambda. Now, if we expand this, we get this result. We can see that the minus 800 and 800 cancel out. And we can see that the remaining terms are all multiples of 5 minus lambda, which is very helpful as we want to simplify this expression as much as possible. We have 5 minus lambda cubed minus 100 times 5 minus lambda. Taking out the common factor 5 minus lambda, we have 5 minus lambda times 5 minus lambda squared minus 100. Expanding the right-hand bracket, highlighted in red here, gives 25 minus 10 lambda plus lambda squared minus 100, which simplifies to lambda squared minus 10 lambda minus 75. This quadratic expression can be factorized, and we see that the determinant of A minus lambda I is 5 minus lambda, lambda plus 5, lambda minus 15. The characteristic equation requires this determinant to be 0, and we can see that we have in this case 3 distinct eigenvalues, minus 5, 5, and 15. Now, we also know that each of these eigenvalues will have corresponding eigenvectors. For the purposes of illustration, I'm just going to pick one eigenvalue. So let's suppose we want to find a unit eigenvector corresponding to lambda equals 5. Well, if we choose a non-zero value for x, we should be able to find an eigenvector corresponding to that x value, which will be parallel to the unit eigenvector we are seeking. So let's take x equals 1. Well, we know that ax must equal 5x, and we can use any of the three resulting linear equations to find y and z. For example, if I take the second equation, we have minus 16 plus 5y plus 4z equals 5y. Subtracting 5y and adding 16 to both sides of this equation, we can see that 4z equals 16, giving us z equals 4. Taking next the third equation, we have minus 20 plus 10y plus 5z equals 5z, which yields 10y equals 20, i.e. y equals 2. Thus, the vector 1, 2, 4 is an eigenvector corresponding to the eigenvalue lambda equals 5. It's now trivial to turn this into a unit eigenvector. We simply divide by the modulus of the vector. Well, the square of the modulus is given by 1 squared plus 2 squared plus 4 squared, which is 1 plus 4 plus 16, which equals 21. Thus, 1 over root 21 times 1, 2, 4 is the unit eigenvector we're seeking. I'm going to leave this example here, but you might find it useful as an exercise to see if you can find unit eigenvectors corresponding to the other two eigenvalues. Eigenvalues and eigenvectors have many applications, but the key reason I've covered them here is their importance in the case of hyperbolic partial differential equations, such as the wave equation, the advection equation, and the shallow water equations. You'll find much more discussion of these problems in other videos on my YouTube channel.